first step, get this down. Second step, be able to deal with the messy stuff. But yeah, it's not a conceptually based test. It's just do you know how to particularly do your and then later and they can use it for things. All right, so our mastery test is next week, Wednesday night, Wednesday afternoon, 4 to 7. It's not a 3-hour test. It's just if you have other things coming and going. I would expect it to take you between like 40 and 45 minutes at the most, reality-wise. So just get there. The room number is on Canvas in one of the announcements. I'm not going to say it right now because I'll say the wrong one for sure, but it's in there, I promise you. It's in an education building, so it's not in this room. But in any case, mastery test is not about do you understand what to do with derivatives. It's just a procedural do you know these facts sort of test. So not like the majority of our tests in here, but make sure you know how to find the derivatives of a variety of sorts of functions. All of these, we're not going to prove all of these in class. Some of them we'll prove later. A lot of them to prove their derivative rules, like all of the inverse trig functions and logarithm functions, and in reality, power function for non-whole number powers involves some techniques that we haven't talked about yet, other sorts of derivatives where the x's and y's are kind of jumbled together. That's not covered on your mastery test. We'll get into that later, and we'll talk about that starting next week, Thursday. But just these basic rule patterns, all of the trig functions, if you understand sine and cosine, I mean, we didn't really prove those, we just kind of justified them. All the others come from those because they can all be expressed in terms of sine and or cosine functions. Logarithms and exponential functions, all the special cases are included in here, natural log and base E exponential as well. Make sure you know those. If you know them off the top of your head quick, then mastery test will take you less than what I said. But there are, on the test, 25 questions that are essentially just one of the functions up here, find its derivative, and that's it. Like, there's not steps to it. It's just, do you know these facts? But the others are the combinations of functions where they're possibly just added, subtracted. Multiplied, divided, and compositions of functions are the more complex ones. So last week on Thursday, we talked about compositions of functions, or we talked about products and quotients. And products, we proved the rule for that. If I want to find the derivative of, or the rate of change of a product of two functions, whose rates of change function I can find individually, we proved it using our trusty rule, the f of x plus h minus f of that thing, just using some algebra trickery, and we came up with this expression. So the one for quotient rule, the proof for it actually involves a little bit of chain rule, but the quotient rule is similar enough to product rule that I wanted to show you that in advance of showing you chain rule. It involves subtraction instead of addition. Again, this is one of the ways that these can be written. I have them all written with the R notation. There's also the prime notation, that little apostrophe mark, or there's that d over dx notation that was on the previous page. But if you have functions combined by like multiplying a known function by a constant, adding or subtracting functions together, multiplying them together or dividing them by one another, we can deal with that. We'll get some more practice at it, but that's what we talked about as of the end of last week. But composite functions are ones that we want to talk about. So if you have something that's like a power function, but maybe it's not just x to the n, it's a whole expression with x, a whole formula or a whole function raised to the nth power. Or what if instead of having just like 5 to the x, I have 5 to a whole function involving x? Those are what are called composite functions, and their rates of change are a little bit messy, but it involves generally finding derivatives of the outer and the inner functions both. The rule for it, if I have a function k that is defined as a composition of g of f, so f is the inner function, g is the outer function, g of f of x, also written this way, then define the rate of change of function k, the composition. I find the rate of change of that inner function, kind of like order of operations, start from the inside and work your way out. Find the rate of change of that inner function, and then find the rate of change of the outer function, but not with respect to x, the outer function with respect to the inner function. So that's the part that's a little bit weird. The notation for it is confusing to look at, or it looks like it doesn't say a lot compared to maybe product and quotient rule. So it's maybe easier to see through a bunch of examples, which we'll take a look at today. But just to kind of show you conceptually, what does this mean? A composite function is when you have two functions performed in succession. So I start with some sort of input value, I apply one function to that, and then I apply a second function to the result of having used the first one. And we've done this when we were dealing with our composition, when we were dealing with our sum, our accumulation sum. We found r of left of x. So left of x is a function that, given any x value, left of x rounded back to the beginning of the interval. And then r of left of x, r of anything would tell us the rate of change at a specific value. R of left of x gives us the rate of change at the left end of an interval. Therefore, so given any x value, doing these two things, find the left end of the interval, and then the rate there gives us one overall output. So just thinking of functions as kind of like machines, I believe this diagram was in your book. If I take a variable x, put this into the left function, what I get out is left of x. I get the x value at the left end. And then I find the rate value that applies to this particular value of x. And what I get out is the end result of having used two functions in succession. Now, the left function is not a continuous sort of function. It's not one that is something I want to find rates of change for. So we're not going to use that in our further examples. But let me just have some generic functions. Let me say we've got what I call them f and g. So looking at these general functions, each of these is composed of some simpler functions. And I can think of doing that composition of functions like f of g of x if I pick the right f's and g's here. So for instance, this function m of x. If you read it, m of x is the square root of, and it's like, oh, so it's a square root function. Yeah, but it's not square root of x, it's a square root of x cubed minus 5, a cubic polynomial. And I know how to find the derivatives of cubic polynomials, and I know how to find the derivatives of square roots of x. This isn't a product of those two. This is a square root of a cubic polynomial. So it's a composition of those two functions. So if I wanted to think about, and let me just get my writing doodad on. If I wanted to think about what it is that's composed here, this takes a few clicks of try again. There we go. So if I want f or g of f of x, is the word that says, so f of x is the inside function, or the first, if you're like substituting in a value for x, first you would do function f to that, and then afterward you'd apply function g, or you do function g. So thinking about this function m here, if I were substituting in a value for x, first I do x cubed, and then subtract 5, and then afterward I take a square root. So in terms of this, the first thing done is the x cubed part, and I can throw on the minus 5. That's actually a composition of two operations, x cubed and then subtract 5 from something, but this is something that we know how to find a derivative of. If this had been its own function rule, f of x equals x cubed minus 5, easy. G of x is the outer function here. So what we see here is g of f of x, and this is f of x. If I wanted to write g of x, I would just have an x in that spot. So g of x, the basic underlying function type is square root of x. In this way, g of f of x would be that expression you see up above. It's square root of a cubic polynomial. So see if you can do the same for the other two. Think about an inner function, which we're going to call f, and an outer function or second step, g. that would allow us to break these down into more identifiable parts, pieces who individually we know how to find derivatives for. So that's e to the 3x to the 8th power, in case that's a little bit small, double exponents. So what about for this p of x here? If I want to think of it as one inner function or first function and then one outer function or a second step, what would be the inner function or the first thing to evaluate or think about in this p of x function rule? Yeah, 3x to the 8th. Thinking about if you were substituting in a value for x, you'd do x to the 8th and then times 3. And so x to the 8th is the underlying function type. It's got a constant multiple of 3. That's not a big deal. We know how to deal with that. P of x, the whole thing, is e to this. So if this is supposed to be g of f of x, and f of x is that exponent, f of x is this, then g of that needs to end up looking like e to the 3x to the 8th. So what's g of x? Yeah, just e to the x, right? E to the x versus e to the f of x, or e to the 3x to the 8th. So g of f of x involves putting f of x in the independent variable spot from g. And either one of these, we know how to find derivatives of those sorts of things. Q of x here, we've got sine of 1 over x squared. Again, if you're thinking about like inner function, outer, like the inner one is the first order of operations wise. What would you do first if you're substituting in a number? Now, on this one, you probably wouldn't be doing this by hand, but nonetheless, you say, okay, so inside the parentheses, figure out 1 over x squared first, otherwise known as x to the negative 2, and then do sine of that. So sine of something, sine of x can be g of x, so that sine of x to the negative 2 is sine of f of x, or g of f of x. So questions on this decomposition of functions. It's kind of pulling these apart to analyze what is put together to make these. So the rule that we have for how to find the derivative of g of f of x, let me jot this down, I'll use prime notation. G of f of x, if I want to find its derivative, start from the inside and work your way out, meaning find the derivative of that inner function, and then find the derivative of the outer function, but like I said, it's not with respect to x, so it's not just the derivative of g of x, it's the derivative of g, but still with that f of x expression in the independent variable position, if you want to think of it that way. So what this would mean for each of these, if I'm dealing with this m here, if I want to find m prime of x, the derivative of m with respect to x, I should take the derivative of f of x, that's the easy part, f prime of x, with respect to x, so just 3x squared, and the 5 drops off. And then I need to find the derivative of function g, but leave f of x in the input variable spot. Or you can find g prime of x, but then replace the x with f of x when you're done. You can think of it either way. Once you've done this a bunch of times, you can probably do this kind of all in one step. But thinking about g prime of x here, square root of x is one of those that was kind of listed as a shortcut. This is really x to the 1/2, and you can use power rule. But as a shortcut that we've talked about before, the derivative of this is 1 over 2 root x, quickly. Same way this one is 3x squared. You can do x to the 1/2 and then say 1/2 x to the 1 lower power, negative half. But just as a quick, because square root show up a lot, 1/2 root x is the derivative of square root of x. Now I don't really want the square root of x here. This is the derivative of g with respect to x. What I'm going to do is then go back to having g of f of x, or put this f of x into this spot here. So I want f of x, not the letter x, in that spot. So I have 1/2 times, not the square root of x, but the square root of x cubed minus 5. So I've got the look of g prime, but not with the symbol x in it. I've got the whole function f of x in those spots where the x would be. So similarly, this one's going to look a little weird just because e to the x, what's the derivative of e to the x? E to the x. All right, so I'm just going to change color so it looks maybe slightly less weird. But 3x to the 8th derivative with respect to x would be 24x to the 7th. I'm just going to combine those coefficients. E to the x's derivative with respect to x is e to the x. So what I want for the derivative of p of x with respect to x is the derivative of that inside function, 24x to the 7th, times something that looks like this, but with f of x in that spot, the 3x to the 8th in that spot. So it's going to be, instead of e to the x, it's going to be e to the 3x to the 8th. Or for the third question here, let's see, what else do we have? Violet. Let's go with violet. Sine of x's derivative, let's see, x to the -2 derivative, -2x to the 1 lower power, -3. Sine of x's derivative is what? Cosine of x. Yeah, derivative with respect to x for this is cosine of x. So when I piece these together, this is the inside function. Its derivative shows up entirely in the derivative of the composite q. Q prime of x includes -2x to the -3 times, not cosine of x, but cosine of, 1/x squared, or x to the -2. Cosine of this f of x, this inner function. So I'm going to write it back as 1/x squared. You can write x to the -2. But what I want to point out about these, there's a variety of ways to think your way through chain rule, or to see the pattern of what you need to write in chain rule. Find something that makes sense for you. If that method I was just talking about makes sense, please stick with it. Try a few things until something makes sense for you. The way that I normally like to think about this is, well, I've got a square root of something. So just like if I had a square root of x, I do 1/2 square root x. If I have a square root of something else, I'm going to have 1/2 times the square root of that something else in my result. Now, when it isn't just an x, that's not the end of the story. I have to worry about what is that something else. Or in this case, it's e to a power. Well, e to the x is its own derivative. E to the something else is almost its own derivative. E to the something else has itself in its derivative, but also times the derivative of that exponent. Or in this case, the derivative of a sine function is a cosine function. Sine of x is cosine of x. Sine of something else is going to have cosine of something else, that same something, in its derivative. But what that something is important. It just shows up as a separate factor. So computation-wise, you can think about working from the outside in, like what's the overall function type, or you can work from the inside out. What's the first function I deal with if I were thinking about changes in x? Either way will get you there. This is just a product of two pieces, but the inner function, the one that has additional stuff done to it afterward, that shows up as its own derivative exactly in the answer here. The outer function has the inner function intact still in it. So I'm going to have a square roots derivative format, 1/2 root something, but it's got the whole mess that was under the square root to start with still there. This 3x to the 8th is still there. This 1 over x squared is still there. So you see that inner function both in its original form and its derivative, in the derivative of a composite function. So there's a couple of pieces that need to be multiplied together. You can write them or think of them in either order. But just make sure that you do have the two pieces and don't just kind of condense it down to, like for instance with m, it's not 1 over 2 times the square root of 3x squared. You don't just get to pile derivatives on derivatives. We have a derivative of an inner function multiplied on separately to the derivative of a square root format. Questions on any of these before I erase anything here? All right, so I already talked about that. So supposing that a function has f, has a rate of change function r sub f, I wanted to go through just kind of a generalization of how this works or why it works the way it does. Not exactly a proof per se with x's plus h's and stuff, but just kind of an explanation of why we need those things. So if I had an expression like this, just to kind of review what rates of change mean, don't forget what they mean. Not important for your mastery test, but for the test that's a couple weeks after, it is, and the rest of the semester, it is. But r sub f of 6.1 equals 3.8. That means the rate of change of function f, when I'm in the neighborhood of x equals, or whatever the independent variable is called, 6.1, this rate of change is 3.8, meaning the y values or the output values are changing at 3.8 times the rate of change of the independent variable. So any small amount that I vary away from 6.1, small amount being the key, the y value of the output will vary by 3.8 times as much. General dy equals mdx sort of formation. So keeping that in mind, symbol-wise, I could write that, here's just with different notation, d f of x instead of dy is mdx, dy equals mdx, or in general, dy df of x equals r sub f of 6.1 dx. 3.8 was specifically this r sub f of 6.1, the rate of change at that specific spot. But this is, we use these constant rates of change to tell us what the ratio of change is from input to output, that m value. So suppose I've got then two functions, f and g. And don't worry so much about the ordered pairs that are here, but just suppose that the rate of change of function f is 5 at some point, 6, 27. And the rate of change of function g is 3 at some point, 27, 14. Now, why those points are mentioned is so we can talk about the input of one is the output of the other. Sort of, we've got a composition of functions we're going to talk about. G of f of x. If I want to talk about the rate of change of g of f of x, the composition of these, whose rates I know separately, 5 and 3, at this, what might be a little bit confusing, but is actually a matching sort of point. I see, so starting with x, we'll start with x at 6. I change x a little bit, so this much. You can imagine it to be like 0.1 or 0.005 or whatever, but starting at x equals 6 and changing x by a little bit, I get this dx. If I'm looking at a function g of f of x, f works first. So f's rate of change will impact the change in the y value associated with this. And so since the rate of change of function f at this point is 5, says it right here, r sub f of x is 5 when we're around this point 6. I change x by a little bit. That means f, the output from the function, changes by 5 times as much, right? 5 times as much as whatever this dx is. So I can imagine this dx extremely small. The change of f, the output to this inner function, is going to be 5 times that amount. Now, what I'm really looking to find is what's the change in g of f of x. So I have to take this result. Now I've changed by what's presumably a slightly larger amount, but if dx is small, then this df is also still pretty small. So the input to this was 6 and the output was 27. So I'm near 27, but this much away right now. So this rate of change for function g, my outer function, should still apply since I'm still near 27. I've moved away from 27 by a little bit because of the inner function. But I'm going to apply this rate of change, and it says, okay, so g changes by 3 times as much as what the input to g changed by. Well, the input to g is this df, right? So the input to g changed by, isn't df, it changed by df. So it's a little bit more than 27 by this much. So I'll use this rate 3 to tell me how much g's output changed. If g's input changes by 5 little notches like that, and the rate of change is 3 to 1, then that means the output for g should change by 3 times this much, which it does. So the output changes by, in this I've got 1 little notch is dx. The output of the inner function is 5 little notches, 5 times as much as dx. The output for the second function is not just 3, it's 3 times 5, because it changes by 3 times as much as the input changed by. And its input was the output of a previous function. Or, in other words, long story short, this is just the visual of what we talked about. I need the rate of change of f times the rate of change of g with respect to x. So, with respect to f. So, the rate of change of f is 5 to 1 with respect to x. The rate of change of g is 3 to 1 with respect to its input, which happens to be f. So what we get is 5 times 3, or I need the change from f multiplied by the change in g due to that change in f. That's that f prime of x times g prime of f of x. It's a little bit messy, but if this kind of makes sense, how first I change f and g changes by 3 times whatever I changed its input by, that's where this comes from. The proof is a bit messy with the x plus h's and whatnot. But here's the R notation again for this. The rate of change of function f with respect to x times the rate of change of function g with respect to f of x, changes in f of x. All right, so again, just different notations, whether it's an R notation, a prime notation, or that d over dx notation, those all mean the same thing. They're all talking about rate of change, or it's that m, our constant rate of change that we've been working with since the first week of class. So, our rule, again, the rate of change of g of f of x involves the rate of change of function f with respect to x, that inner function, its derivative just normal way, times the rate of change of the outer function with the inner function left intact or substituted in, however you want to think of it, in place of what would have been the independent variable if they weren't composed. So this is just the words I was saying, highlighted in bubbles here. So the rate of change of g of f, the composite function, with respect to x, is the rate of change of f of x with respect to x, multiplied by the rate of change of g of x with respect to f of x. All right, so as said before, you can think of those pieces in either order. If you want to work your way outward in, you can do that. If you want to think about starting from order of operations inside out, you can do that. It is just 2 pieces multiplied together. So I could write them in the other order, it's fine. Not a big deal. I would suggest don't try to simplify or distribute anything. Just write out the parts. Don't do algebra. Just write out the rules and stop. So let's look at a couple more examples. We already did those. Here we go. So I've got a composite function, or several composite functions, on the left here. They all involve an inner function and an outer function. The last one has a big mess. So start at the top. Take a bit of time, compare notes with a neighbor, but see if you can work through how to find the derivative of each of these functions called capital C. They all involve chain rule, or this compositions rule for finding derivatives. And some of these involve some individual function types we haven't specifically gone over in lecture yet, but they are all on that list. And we're going to go back and talk about quotient rule again. so let's take a look at these. So the first one says c of x equals cosine of natural log of x. So we haven't talked about natural log of x yet, but if you just had a function y equals natural log of x, what's y prime? Natural log of x's derivative. 1 over x. Nice, simple looking derivative. Maybe we'll prove that one later. It involves slightly weird trickery, but it's a simple enough format. We'll take a look at it. So when we're looking at the derivative for c of x, natural log of x here is the inside function. It plays the role of f of x in this. So we're going to see both natural log, probably still in parentheses, and also natural log's derivative multiplied on as a separate factor. So cosine, we talk about cosine functions. Their derivative of cosine of x is sine of x with a negative multiplied on, negative sine of x. So the derivative for c of x is going to involve a negative sine function, and it's also going to involve a derivative of a natural log function. So if you want to, lost my, restart this guy since it's being difficult here. There we go. Since I know it's going to, ooh, there we go, even scarier stuff. All right, so if I want to think about this in terms of breaking this down, kind of maybe work carefully through it, the inside function, the f of x, there it is. The inside function, the f of x, would be natural log of x. And the outside function is g of x would be cosine of x. G of f of x is cosine of natural log of x that way. So the derivative of function c involves the derivative of the inner function, this natural log of x, which we said would be 1 over x. I just wrote it first, but it doesn't matter. And then we need the derivative of the outer function, but with whole f of x, natural log of x, as the independent variable spot, or in the independent variable spot. So negative sine of x, but instead of having an x there, it's going to be negative sine of natural log of x. So the original inner function still intact. And again, you could write this in whatever order, and that looks kind of like an E with my messy writing. That's a natural log of x. Ooh, it looks like an E or an I can't win. Natural log of x as the input to this sine function, which is multiplied by -1. And of course, there's lots of different algebraic ways you could write this. You could write it all as one big fraction, but there's no canceling that can happen, so just put the pieces together and then stop. Don't worry about algebra. So if you're going to do anything, if you have multiple coefficients, maybe throw them together, but no need really even to do that. So in this one here, I've got a logarithm and a trig function, but the other way around. This time the inner function is the sine function, whose derivative is regular, not negative, cosine of x. Or, yeah, sorry, I was writing sine of x and saying cosine, confused myself. The outer function, g of x, would be log base 5 of x. Logarithmic derivatives, natural log of x's derivative is 1 over x. Log base 5 of x is just a multiple of that. It still involves a 1 over x in the denominator, although, here I'll write this, g prime of x is going to have an x in the denominator. What else is in the denominator besides an x? Yeah, natural log of 5. It's got a numerical factor in the bottom, because the difference between log base 5 of x and natural log of x, they're just different bases, but they're relating a base number via exponent to that input that you see, the x. So they're just off by a constant factor, although it's a factor in the denominator, so a smallish looking number. This is natural log of 5. And typically it's written this way with the natural log at the end, so you don't have to put so many parentheses. You don't want to have it look like natural log of 5x. It's an x times a natural log of 5, or an x times a constant in the denominator of this. So that's g prime of x. What we want for the derivative of this function c here is g prime of f of x. So I'll write it in that order first. So g prime, but with f of x instead of x in that spot. So it's going to be 1 over f of x with sine of x. So 1 over sine of x times the natural log of 5. And then times f prime. F was a sine function, just plain old sine of x. So f prime of x would be, as we said before, cosine of x. And of course, you could write the cosine on the top if you wanted to. You could do trig identities and say it's, I don't know, cosecant or cotangent times 1 over natural log of 5 or something. But you just leave it like this. So again, I wrote these in the 2 different orders, one with g prime of f of x first and one with the g prime of f of x second. Doesn't matter. Just make sure you get the 2 components to chain rule both in your answer. So this next one here, this is just squared. If you wanted to multiply this out, you could do distributive property, multiply square root of x plus e cubed times itself, and then not have to do chain rule. But if you don't want to deal with that, you can use chain rule. So sometimes you have options in how to approach a problem. There's not a way to simplify down like this to something that doesn't involve a cosine of something. I mean, you could use trig identities and write it something differently, but it's still going to be a cosine of not just an x. It's going to be a cosine of a function involving x. Or possibly cosines and sines if you get crazy with trig identities. But for this function right here, square root of x plus e cubed, if that were on its own, we could just take a derivative of that easy enough. It's not a polynomial, but we've got a sum of a power function with a constant, so pretty easy to find a derivative of. But then that 2-term expression is squared. So the derivative is in part like x squared's derivative is, and it's in part like, well, square root of x's derivative is. So the inner part, the f part, is the square root of x plus e cubed, which remember e cubed is a constant, e is a constant. There's no variable in the exponent, so this is just some number, like 30-ish or something probably. The outer function g of x would just be x squared. We have g of f of x would be this. So individually, the derivative of this inside part, that's our 1 over 2 root x, yay, plus 0 if you want. The derivative of the outer part would just be 2x to the first power if it were g prime of x, but we want not 2x to the first power, but 2f of x to the first power. So you don't have to write first powers, so there's other ways you could write this, but just to demonstrate what all is going on here, we'd have these 2 factors. 1 over 2 root x, the derivative of the inside function, times 2 times this 2-term expression to the first, the derivative of that squared, that outer function, with respect to the inner. And again, there's tons of simplifying that could be done here. If you can see this, there'd be no, so I'd have 1 over 2x, or 1 over 2 root x times 2 root x, okay, that's 1, plus 1 over 2 root x times e cubed. So this all simplifies down to e cubed over 2 root x. If I were to change this to like a 17th power though, using the method we just talked about, the only thing different about this would be just the coefficient and that exponent. So like I said, if this were a 17th power, then this would just be 17 and this would be 16 and the rest of it would be the same. So in terms of how you can use the same approach over and over, because this was a second power, there are a variety of different ways you could simplify it or do it without chain rule, but if it was any other power, we could still use the same method with chain rule and it would be just as easy. Not as easy as maybe squaring something is, but that wouldn't change the general idea of this one too much. So, all right.
I'm going to put that back to this because I've got another problem where I want to use that. Can I move this? I don't know why it won't let me move it. Well, there we go. Scoop this over here. All right, so the other expression on here, if you see this, we've got a bunch of things coming up. So the 6 times 7 to the tangent of x power. The 6 is just a coefficient, the constant multiple of this 7 to the tangent of x power. So looking at this, I don't have to worry about product rule. You can use product rule on any product you want, including just like 2x. You could do product rule with that. But it's unnecessary when you have a constant factor because, well, what I was just talking about, if I had 2x, and I think of this as a product of 2, the function, and x, the function, the derivative of the first factor here is 0, and the derivative of the second factor is 1. If I use product rule, I'd have 0 times x plus 2 times 1. 0x plus 2, which is just 2. Whenever you have a constant multiple, if you try to use product rule, you'll end up with 1/2 of product rule disappearing because of that constant factor's derivative being 0. But in any case, for this 6 times 7 to the tangent of x power, that 6 is just this coefficient or constant multiple. So if I'm thinking about the derivative of it, I don't have to worry about too much. I'm going to say, okay, so it's going to be 6 times what it would be otherwise. I'm going to worry about how do I find the derivative of 7 to the tangent of x power. It's got this tangent of x, which we haven't really talked about the derivative for maybe we did. I think we did this right at the end of class on Thursday last week after talking about sine and cosine derivatives. The derivative of tangent of x is secant squared, otherwise known as 1 over cosine squared, of x. Since it's tangent of x, its derivative is secant squared of x. Now, this is the inner function, f of x. This is f prime of x then. I'll label it. The outer function is the, well, 7 to the something. So 7 to the f of x. So my outer function, g of x, is a base 7 exponential function. G of x is 7 to the x. G of f of x is 7 to the tangent of x. But the derivative of 7 to the x, we talked about this last class also, involves itself. It's not quite as easy as e to the x, but it's 7 to the x times a constant factor, natural log of 7. So the derivative of the outer function, basically, g of x is 7 to the x natural log of 7. If I have g of f of x and I want to find a derivative, I need that rate of change function for g, but with the whole function f of x in that spot there. So I need tangent of x still in the exponent, in other words. So I've got 6 times 7 to the tangent of x times natural log of 7. So this is that r sub g of f of x, or g prime with f of x in the independent variable spot. This is just a constant coefficient of 6. We're just kind of carrying that through. It just stays multiplied on, or it scales up the steepness, visually speaking, from what it would be without that 6 multiplied on. But I still need r sub f of x, the derivative of tangent. We haven't put that in here yet. We thought about it earlier. The derivative of tangent of x with respect to x is just secant squared of x. So this lovely thing, it's just a bunch of things multiplied together. 6 constant multiple. 7 to the something times natural log of 7, that's the pattern for exponential base 7. So it happens to be 7 to the tangent of x times natural log of 7. And then here's the derivative of tangent of x, secant squared of x. So r sub g of f of x and r sub f of x are multiplied together with these f's and g's, and this was just an extra multiplied on, just a constant. So you don't have to name that or call it part of the exponential function or part of the anything else. You can say, oh, that's just a constant multiple. Just it multiplies onto the function as it would be otherwise. Now, the last expression here, you can see is just a combination of some of the others. I've got a square root of the expression that we just found a derivative for minus the first one that we found a derivative for. So all the pieces and parts are already here, although it's quite messy to put this all back together. But if you see here, it's like, oh, I've got a square root of something. So I've got a composition of functions, but what's underneath also contains compositions of functions. So we've got two levels of this. There could be more and more, like you can put together as many as you want. Realistically speaking, how many different things are we going to have composed on one another depends on how many steps long your process is. But I'm going to clear all this off, kind of start from scratch and talk all the way through it. So outermost function is this square root, right? We know to do a derivative of a square root function, it's 1 over 2 times the square root of something. So I'm going to say 1 over 2 times the square root of, well, all that. So I'm just going to write it quickly. 6 times 7 to the tangent of x. That's tangent. Minus cosine natural log of x. There we go. So I've got, this is the derivative of the outermost function with the inner part still all intact. But now I have to think about, well, how do I find the derivative of this inner part here? So it's in multiple layers, but the inner part is all of the stuff that's underneath that square root function. And it's 2 terms. So, oh, I know how to find the derivative of something with 2 terms. I just do each one separately. I'm going to multiply on the derivative of those 2 terms, which I'd have to write them both out. They'd still be subtracted by the time I'm done. And the 2 halves of that subtraction are things that we previously worked out. The derivative of 6 times 7 to the tangent of x was kind of a mess, but it was 6 times 7 to the tangent of x times natural log of 7, and then times the derivative of tangent of x, which is secant squared of x. So this is all things multiplied together, minus the derivative of cosine of natural log of x, which we said was 1 over x from the natural log part, and the derivative of cosine is, oops, negative sine of same thing it started as, natural log of x. So a little bit of a mess, but this was our answer to the very first c of x example. This was the answer to the 4th one. And the answer to the 5th one is, well, involves square roots like we did here. 1 over 2 root something, but all the something is the same something it was before. Just like this, if you see sine of natural log of x, when you take a derivative, there's going to be a cosine of natural log of x. The inside parts of the functions, when you're just taking the derivative of the outside, the inside stays intact, or it stays as it was originally. So the derivative of a whole big polynomial to the 17th power is going to involve that whole big polynomial to the 16th power times 17 and times the derivative of whatever the details of the polynomial were. So there's a lot of steps to some of these. Something like this question, this last one, might be an example of one of the harder ones from your mastery test. So like I said, there's 35 questions altogether on your mastery test. 25 are like just off of the list of, hey, find the derivative of natural log of x, find the derivative of secant of x, find the derivative of arc sine of x. Just something off the sheet. 25 like that, easy. The other 10 are not all like that. That's like the hardest few, maybe, would be something like that. There are going to be some others that are maybe along the lines of just this, or just a product, or just a quotient. Something that's a little bit kind of in between. So there's 25, I'd call it 25 easy, 7 medium, and 3 hard. Yeah. No, All you have to know is, can you put together the result? And you no simplifying either, just leave it as is, doesn't really matter. Yeah. Mm-hmm. Nope, just leave it like that. Yeah, don't worry about doing algebra, just do the calculus part and stop. Yeah, because I hope that you could simplify some of these. Some of them don't really simplify, but that's not what I want you to be tested on. I just want to see the calculus part, and I don't want you to make any mistakes accidentally on the rest of it, nor do I want to have you spend time doing all the rest of that either. Just apply the original calculus derivative rules as they are. Whatever order you want to write the pieces to it in is fine, but don't do extra steps to try to make it look nicer. You just leave it as is, as kind of messy problems. So you see, we did these 5 questions, and first time through looking at some ugly things like this in not too long. On your actual test, you'd have a total of 10 more challenging than what's on your just memorize these lists, of which only like 3 or maybe around this difficulty level, and the other 7 are closer to these or product or quotient rule with basic parts. So let me show you a few more examples of what I mean by that. Ooh. Sorry, I'm trying to find what I'm looking for here. Do I have them? I don't think I have it on there. All right, so let me just start with this one. So this is the list I was talking about. I had this up at the start of class today also. But just these, like 25 questions are just straight off the sheet. Maybe has a coefficient, just as have some things that makes it look interesting, but mostly no. Product rule, you take the derivative of each part, but then you multiply it by the other original part, and by part I mean factors, functions that are pieces multiplied together. If you have a quotient, just remember that there's subtraction, the order is kind of important. Whatever the derivative of the numerator is, that ends up in the first half of the subtraction. The derivative of the denominator ends up in the second half of the subtraction. And there is a denominator. We end up with a fraction still by the time we're done. And the denominator of the derivative is the square of the denominator of the original function. Unless you simplify in something. But we're not going to simplify, so it'll just look like this. And then as we were just talking about, compositions of functions, kind of harder to explain because it's not just f prime of x and g prime of x, it's f prime of x and g prime of f of x multiplied together if f is the inner function. So the questions on the left are things that you could possibly see in the first 25, secant of x, log base 2 of x, pi to the x, arc cosine of x, x to the e. The ones on the right, kind of like medium to difficult, hard, would be among those other 10 questions. But take a look at, let's see, yeah, we've got 18 minutes. So see how far you can get with these, especially like 1 through 7 particularly. 8 takes a little bit longer, just like the last one that we did. So you can figure out these. If you're not confident with what's the derivative of secant, it's okay, got a little bit of time, but see if you can find it someplace. I'll talk about some of this, and then I want to talk about what is the quotient rule. things like 6, 7, and 8 that look like a mess, make sure you think to yourself, what's the overall structure of this? Like, there's lots of pieces. Is it a product? Is it a quotient? Or is it a composition of functions? Or some combination thereof? Alright, so this first one, y equals secant of x. Nothing specific about that one, it's just straight off the sheet. Do you remember what the derivative of secant of x is? Yeah, secant of x times tangent of x. Yeah, so don't forget the x's when there. It's really, in your head, it's fine to say like derivative of secant is secant tangent, but secant and tangent both have to have inputs to them. So if this is secant of x, its derivative is secant of x times tangent of x. You don't have to write time signs. You don't have to write parentheses. It's understood what all that means. You will see it sometimes with more care taken to how it looks, but secant of x times tangent of x is the rate of change rule. That can be derived directly from knowing secant of x is 1 over cosine of x. If you think, oh, cosine of x to the negative 1 power. And so I could find the derivative, negative 1 times cosine of x to the negative 2 times the derivative of cosine of x, which is negative sine. The negative signs drop out. We've got a cosine in the denominator, and this is a sine over cosine, so it's a sine and a cosine to the negative 2. It's just, this is a standard way that you'll see these written because it's quick to write them without denominators by using those reciprocal functions. If you happen to have them memorized in other formats, that's fine. If you want to say instead of secant times tangent, if you want sine over cosine squared, that's fine. Up to you. Let's see, log base 2 of x. Well, we did a log base something else, 5, I think, on the other page. But log base 2 of x has a derivative with respect to x that involves 1 over x, just like every other log function. And then natural log of 2, also in the denominator. So far, so good? All right, now, things that are easily confused with one another, especially when they're strange numbers. Things like number 3 versus things like number 5. Notice the differing locations of the variable x. So these are all going to be functions with respect to x. We're not going to switch up the variables on you and have something else like t's all of a sudden. It's just x's. So when you see the x's, remember x's are the variables. Anything else is not a variable. So pi to the x power has x in the exponent position, has our variable in the exponent position, making this an exponential function. It's similar to 3 to the x, but just pi is a little bit bigger than 3. So what's the derivative for number 3? Y prime equals, want to take a guess? Yeah, pi to the x times the natural log of pi. We don't subtract 1 from the exponent unless that's a numerical exponent, like it is in number 5. This is a x as the base of the exponent and a number, 2.7-ish, as the exponent. So when I take the derivative of this, this is slightly less than x cubed. It's going to be slightly less than x squared by the time I'm done. Yeah. Oh, yes, it should be. Sorry. Thank you. I'm talking and writing at the same time. Natural log of pi. Apologize, yes. Yeah, it's always natural log of a number that shows up in these logarithmic and exponential function derivatives. So skipping to number 5 for just a second, because it's similar to 3 but not the same. X as the base is, well, this one's probably not what you think of as a polynomial, but, well, it's a monomial. It's a power function. So just like x squared or x cubed, to find the derivative of x to the e, which is x to the 2.7-ish power, I have x to 1 lower a power, e minus 1, all multiplied by the old power, e. So e x to the e minus 1, approximately 2.7 times e to the 1, or times x to the 1.7. Now, skipping back to arc cosine, otherwise known as inverse cosine. So there's 2 different notations for that, but arc cosine of x, derivative involves a lovely fraction. We'll talk about inverse functions and maybe logarithms and how their derivatives come to be, maybe a little bit on Thursday. But if I want the derivative of arc cosine, at this point, just as a memorize it or see it listed someplace, has it got a negative or does it not have a negative overall? Yeah, it's got a negative, just like derivative of cosine has a negative, derivative of arc cosine has a negative. 1 over square root of, is it 1 minus x squared or x squared minus 1? 1 minus x squared. The way you can keep those straight, and the way I remember, this isn't something that shows up a lot, even in math teacher life. Arc cosine, remember, is a function that takes an output from a cosine function and gives you back like the angle that pertains to it. So outputs from cosine functions are -1 through 1. So the only values of x that should make sense as inputs to an arc cosine functions are -1 through 1. Now, we would exclude exactly equal to -1 and 1. That would make a denominator of 0, but all the numbers in between are the sorts of things where this square root would be defined. All right, so just looking quickly at the ones on the right, and we'll talk about these in more detail on Thursday. But thinking about if I want to find the derivative of this, what general way are the pieces of this function connected? Yeah, this is a product. So I know how to find the derivative of a tangent of x. I know how to find the derivative of an x squared. If they were just individual parts. They're not. They're stuck together. But they're just stuck together with multiplication. So although it's messier than just addition or subtraction would be, if I can find, I'm just going to kind of shortcut here, the derivative of the 2 pieces separately, 2x, and derivative of tangent we did earlier was secant squared of the same thing. So if I need to find the derivative of this whole function y, the derivative of the first part times the original second, plus, other way around, derivative of the second part times the original first. And again, those products you can write in whatever order, sums you can write in whatever order. The next one is maybe more obviously a quotient. The numerator has a couple of terms, so natural log has a coefficient on it, but nothing like products or quotients that we need to use in the numerator of this fraction, and just a polynomial in the denominator. So if I'm thinking about the derivative of the numerator, I know the 5 would go away. The 6 is just a coefficient on natural log of x. So I can write that as 6 times 1 over x. That's one of the things that is pretty easy to combine, and lots of people do just call it 6 over x, but you don't have to. The derivative of the denominator on its own would just be 2x. The -1 is a constant, it drops off. So to find the derivative of the fraction y, the quotient, I know that my denominator is going to be original denominator squared. You don't have to multiply it out, just x minus 1 quantity squared. And the derivative has in its numerator, the numerator's derivative, I'm going to write it the short way to save space, times the original denominator minus other way around. 2x times 6 natural log of x plus 5. Make my fraction line a little longer, and there we're done. So the last one, like I said, we'll talk about that one next time, but it involves a 1 over 2 times the square root of something times the derivative of something. So anything of this form is going to have that sort of format for it, star being an official mathematical notation. But if you just have a mental way to think of what you need to do, you can fill in the blanks later with the details. All right, so what I wanted to talk about, last thing before we leave, is just in general about quotient rule. We just did an example of quotient rule. We said that if I have something of this form, our quotient rule looks like f prime times g minus the other way around, all over the denominator squared. And we did a pseudo proof of this using just product rule on last week, Thursday. The only thing is, it kind of skipped a couple of algebra steps because it involved chain rule. If I write this as f of x times g of x to the negative 1 power, thinking about chain rule, now that we've actually done this, and I think, oh, well, this is just a product. The derivative of something that looks like that would have the derivative of f of x times the original g of x to the negative 1 plus, all the way around, the original f of x, I'm just saving the worst part for last, times the derivative of this. I've got a whole function raised to the negative 1 power. Thinking about chain rule, that's negative 1 times whole function raised to 1 lower a power, and then the rate of change of that inner function, g prime of x. This is actually algebraically equivalent to that. This is the part that is kind of said last time, said, we'll talk about that next time, so this is next time. Simplifying this a little bit, notice this second term here has an f of x and a g prime of x and a negative 1. So it's got an f of x, a g prime of x, and a negative 1. The first term was, well, it's got a g of x raised to the negative 1. So I'm going to write in this fraction. This has g of x to the negative 1 power. This term has it to the negative 2, which would be that. If I want to make these like terms so that I can do this subtraction, I'm going to make common denominators by multiplying on g of x, so the top and the bottom both. And then you can see our familiar look. F prime times g minus f times g prime all over g of x, oops, squared. So if you'll believe in product rule, which we went through the proof of that last time, quotient rule also works, just using a little bit of algebra and chain rule. Chain rule, the mysteries of it are a little bit messier. Maybe we'll talk about that another day. But what we are going to be able to do is, we talked about, if you believe me that y equals a to the x has a derivative that is y prime equals a to the x times the natural log of a, also sort of involves some weird algebra. Log base a. Now, this expression here is exactly equivalent to log base a of y equals x. If I ask you to find y prime from this, it's kind of weird because y is jumbled into the middle of it, but you can find the derivative of the terms that you see, and y prime will turn out to be one of the pieces of that expression you get. You can solve for y prime, just kind of like algebra question. There's a x's all over the place that says solve for x or find x. It means you have to isolate it. Doing things like this actually involve chain rule. We're going to talk about a little bit of this next time. How do I find y prime if y is trapped in the middle of an expression? Now in this case I could rearrange it and make it look like an exponential expression. sometimes rearranging it makes it into something that I'm less familiar with, so there's other ways to go about it. And that's what we're going to talk about a little bit next time, along with some other kind of review of what all derivatives are for. But I think we've talked about a lot of chain rule today, so I hope that you feel a little bit more confident with it and have some more examples to work from. All right, I'll see you Thursday. Yes. This week, yes. Yes. Whatever it says on your schedule. I think it's skipped next week because that would be for some of you at the same time as the master exam. And yeah.